Hello once again, class. In this video, we're going to talk about annuities, particularly savings annuities, and how they play a role together, kind of with compound interest. And we'll talk a little bit about the concept first, as always. First things first, savings annuities are the practical way to save for the future. Not a lot of us can just deposit large sums of money into a savings account, at any given time. So typically, you subscribe to some kind of retirement plan, like a 401k or an IRA plan. Those are examples of annuities. And what they do is they take money from each paycheck that you get, and then they deposit that specific amount of money into your savings account. And remember that savings accounts generate their own interest with compound interest stuff, whether that's monthly or daily. Those are probably the two most popular ones with banks nowadays. But when you combine it with an annuity plan, there's really two ways that a savings account generates growth. One is the compound interest, and then two is the deposit that is made from the annuity plan, right? It takes money out of your paycheck, puts it in that particular savings account. Annuity, basically the same thing as compound interest, except that it's happening, like you're depositing money every single month. Whereas with just regular compound interest, you just deposit money into an account one time and then you just let it sit there and kind of grow interest. But with an annuity plan, you're putting money in it each month, and that money that you put in each month starts generating its own interest at the same time. Deriving the formula for this thing is a little bit tricky, so I want you guys to kind of buckle up here. There's a little bit of stuff to go through. I'm going to try to make this as easy as I can. We're going to use an example to set this thing up. And the example is this. Suppose we set up an annuity account that takes $100 from each monthly paycheck that we earn, and it puts it into a savings account with a 6% APR that is also compounded monthly. So we're depositing at the same frequency that we're compounding in this example. And the first thing that we should do is note that 6%, that's an APR, and it's happening 12 times per year, right? So we do the math here, 0.06 divided by 12, that's 0.005, which is just the normal compound interest, right? That's just the 6% APR broken into 12 pieces. But the thing that makes this tricky is that we're continually depositing $100 into this account every month. So let's kind of see what that would look like. So first thing that I want to do is write down here that our initial amount, we're going to pretend that our initial amount is $0, right? There's nothing in the account initially until that first paycheck comes, and then we take $100 and we put it into the account. Okay, so P1 is going to be equal to P0, which is just $0, right, is what that is, times 1 plus 0.005 plus 100. Right? Now this whole thing is 0 because P sub 0 is just 0, so that's just gone. So it shouldn't be a surprise that after our first paycheck, and interest is compounded, but remember that the compound interest is based on $0 at the beginning. So we've just essentially deposited $100 right into the account. And that's it, right? That's how much we have at the end of the first month, right after our first paycheck. Nothing to build interest off of. Well, now there is something to build interest off of because now there's money in the account. Right, so when P2 rolls around, we're going to take the value that we had at P1, which is $100, and I'll write that here in a second, and then multiply that by 1.005, which is 1 plus 0.005. And then we're going to add $100 to it. Okay, well, P sub 1, remember, was generated by this whole thing up here. Right? So I'm just going to, because I want us to see a pattern, I'm going to do a little bit of a substitution. I'm going to substitute that thing in for P1, right? And so what that's going to give us is P sub 0 times 1 plus 0.005 plus 100. But then that thing is multiplied by 1.005, which is this one that's just hanging out, and then plus 100. Okay, again, this thing is just 0, so this ends up just being the 100, that's an equal sign, 100 times this piece, 1.005, plus 100. All right. This thing ends up being 100.5, and then we're going to add 100 to it. So we end up with an amount, as a dollar amount, that's 200.5. Okay, so that's the amount that we have in the account after 2 months. All right, let's see what's going on at 3 months. And this is where things are going to start to get a little bit crazy. But again, I'm going to try to keep everything as concise as I can. First and foremost, all we're doing is we're taking the amount that we have in the account, which we're going to symbolize with P sub 2, which is actually the 200.5 over here. And we're just going to multiply that by 1.005 plus 100. Right? So it's the same thing every time. It's the previous month's value times 1.005 plus 100, right? Previous month's value times 1.005 plus 100. Previous month's value times 1.005 plus 100. But we're trying to figure out what the pattern is so we can come up with a formula. All right? So again, I'm going to substitute the thing that we used to calculate P2, which I think I'm just going to put in, let's go with this one. Right? That's what it's going to end up being. Okay, let's do that substitution. So if we substitute all that in for P sub 2, we're going to get 100 times 1.005 plus 100. Okay, and that's P sub 2. Then this thing is still there. So times 1.005 and then plus 100. Okay, is what we're going to get there. All right, well, at this point, I want to do a little bit of distribution. Right, so I'm going to distribute this 1.005 through this kind of bracketed expression here. Okay, and what we're going to get is 100 times 1.005 squared plus 100 times 1.005 plus 100. So you notice there's kind of a pattern that's emerging here. This 1.005, it's almost acting like a variable, right? In fact, this is almost kind of like a polynomial. You got a squared term raised to the first term and then a raised to the 0th term, over here. But the point is 1.005 is decreasing in power as we move along the expression here. That is not a coincidence. That's actually the thing that's going to help us come up with the formula here. Okay? P sub 4, I'm going to spare you guys the algebra. But what you're going to end up getting is 100 times 1.005 cubed plus 100 times 1.005 squared plus 100 times 1.005 plus 100. Okay? And the reason that this is happening is because this 100 here, that's this thing. That's this 100 that's now gone through 3 iterations of gaining interest. This 100 here, right, that's, where is it? That's this one. Right? Now it's gained 2 months of interest. This 100 here, that's the previous month's 100, gaining only 1 month of interest. And then this 100 here is the constant 100 that we're putting in, hasn't gained any interest yet. Okay, so the formula that we're going to be able to come up with for this thing is mostly recursive at this point, mostly recursive. And what we can say is that P sub m is going to be equal to 100 times 1.005 to the m minus 1 plus 100 times 1.005 to the m minus 2. And we're going to just be able to do this until we get down to 100 times 1.005 plus 100. All right? Which doesn't really look like a pretty formula, right? That looks pretty messed up, actually. What I'm going to do, though, is I'm going to take this expression, this equation, this whole thing, and I'm going to multiply both sides by 1.005. So this whole thing gets multiplied by 1.005. So this is actually being distributed, right, to all of these terms, inside of here. And what that's going to give us is on the left-hand side, 1.005 P sub m, right, which stands for the amount after some amount of months. That's why I'm using m here, is equal to 100 times 1.005 to the m plus 100 times 1.005 to the m minus 1, all the way until we get down to plus 100 times 1.005 squared, right? Because this has been multiplied now by 1.005 again. And then this 100 is 100 times 1.005. Everything got multiplied by 1.005. And what we have here is essentially a system of equations. Okay? The first one being the one that we just found, right? The second one being the original one, right? P sub m is equal to, and I'm going to actually write it like this, kind of staggered, because this is the original formula that we came up with. You know, and it goes all the way down to, let's see, actually, let's just come over here so I can line it up correctly. 100, 1.005, and then plus just the 100. Right, that's on there. And if we do some subtraction, right, if we subtract the two left-hand sides together, if we subtract all of the right-hand side stuff together, notice that all of this stuff, because I aligned like powers here, all of this stuff cancels. So what you're going to be left with is just this minus 100 on the right-hand side. 0.005 of some variable minus 1 of some variable is only going to leave 0.005 of that variable. And then all we have left on this side is that. Right, and it's minus 100, by the way, because we're subtracting positive 100 here. So minus 100. Okay? And at this point, we are almost done with the formula. All I'm going to do at this point is pull out a 100 on the right-hand side and divide everything by 0.005, and that's going to give us this formula. 100, pulling that out of there, so we're going to be left with 1 plus 0.005 to the m minus 1. And actually, let me go ahead and put this in brackets here. And that's all divided by 0.005. By the way, kind of a weird thing that I did here, I, for some reason, broke up 1.005 into 1 plus 0.005 just to separate the rate again, because that's more how the formula is going to be. But again, in this case, very similar to when we were coming up with the formula for compound interest, we don't want to just use m here, right? M represents the number of months that have transpired, same as this thing. So instead, we can replace the m, with a number of years times however you're compounding. We can replace the m, right, with just an n to represent years. We can replace the 0.005 with a rate that's divided into the number of compoundings, right? That's what this thing is going to be. Same with this part. And then this, we're going to actually give the variable name d to represent our deposit per month. And that essentially is the formula for this thing. So here it is. Okay, P sub n is equal to our deposit times the quantity of 1 plus, and this part should look familiar, right? This is essentially compound interest. Part of it anyway, right there. Then we're subtracting 1 from it, and we're dividing it all by how we're distributing the rate over the number of compoundings that's happening. Okay, so let's do an example. And I hope to show you that this formula isn't used really any differently than like a compound interest or even a simple interest type of formula. It's all just formula based, right? You need to know what your variables are. You plug them into the formula, and then you can figure out, what it is that you're trying to find. So this is a very straightforward example. This one says a traditional individual retirement account, which is also called an IRA, is a special type of retirement account in which the money you invest is exempt from income tax until you withdraw it. If you deposit $50 a month into an IRA earning 4% interest, which we're going to assume is also compounded monthly, how much will you have in the account after 30 years? So let's just plug in some stuff, right? We got to figure out what is our deposit, right? Our deposit's 50. We got to figure out what's our rate, right? Our rate is 0.04. We're compounding monthly. Right, so I'm just filling out the details of this thing. And then, what are we missing? Oh, N is 30. right? We're just going to plug all this stuff into our formula, which remember is this, D times 1 plus R over K. That quantity is raised to the NK. We're subtracting a 1, and it's all divided by R over K. All right, so I like to call these things plug and chug, right? You plug in all your information. That should actually say 30. I'll just start over down here. P sub 30 is going to be equal to 50 times 1 plus 0.04 divided into 12 pieces, raised to the 12 times 30 minus 1. And that's all going to be divided by 0.04 divided by 12. And you just plug that in, right? I'm not going to go through all this stuff here. You literally plug it into your calculator, and you're going to get $34,702.47. Now, I just want to, that's the answer, and we're done at this point. That's how much we're going to have after 30 years. But I just want to point out that in order to get this amount, right, and this is the cool thing about IRA accounts, in order to get $34,000, all you had to do was pay $18,000. And how I'm getting $18,000 is because you're just investing $50 a month for 30 years. 50 times 30 times 12 is 18,000. You're giving the bank 18,000, but you're getting back 34,000. Right? That's the power of an annuity. All right, so let's do another example. Suppose you want to have $250,000 in your account when you retire in 25 years. Your retirement account earns 7% interest compounded monthly. How much should you deposit each month to meet your goal of $250K? Okay, now in this example, we're looking at 25 years. So P sub N is really P sub 25. And we know that we want to end up with $250,000. What we don't know in this example is D. Right? We don't know the monthly installment. Okay, we know N is 25. We kind of already covered that. K, we're compounding monthly. So K is going to be 12, and then our rate is 7%, but as a decimal. Okay, we plug all this stuff in to our annuities formula. We're looking at 250,000 is equal to D, which we're solving for here, times 1 plus 0.07 over 12, raised to the 25 times 12. I think 300 raised to the 300 there. And then this whole thing is divided by 0.07 divided by 12. Again, all right, and so what I went ahead and did is I calculated essentially this whole thing. Just ran it all through my calculator. I wanted to know what we're multiplying D by that's supposed to get us $250,000. And so what I ended up with, 250,000 is equal to D times 810.0717. I think I rounded that number right there. I think it was like 6.8 or 6.9 or something like that. But okay, look, we've got 250,000 is equal to D times some number, right? If we want to undo a multiplication of 810 with some change, we're just going to divide by 810. Essentially, multiply by the reciprocal. All right? And if you do that, what you end up with here is $308.61. All right? So I hope you guys found that helpful. Until next time.